I haven't even tried one.
Oh, all right, but these questions are in.
Yeah?
The point is that you guys already let's just put
Get through the process.
Okay, so how's the project progress going? Is it going well? Does anybody have any problems with the project?
I just found weird the fact that the distance between columns, like the parametrical ones, are like 1.5 meters. Like, I'm going to assume that actually that model will be like the little, ¿cómo dice maqueta en inglés?
Oh, you mean the spacing between the center line or the edges?
No, between the edges, that they're like super close.
Yeah, well,
Like a model. Yeah, so I'm going to assume that actually that project, it will be like a model. Like, for example, the one that architects usually do for the projects, like with pieces of wood.
oh yeah, you are saying you have 1.5 meters spacing center to center, right?
No, it's from
Edges.
edge to edge.
Edge to edge?
Yes.
Yeah, that's fine. 1.5 meters is okay.
Okay.
Yeah. So usually, these buildings, these things become like windows, you know, like the 1.5 meter, that's how the tube system is. Yeah, sometimes it looks a little bit ugly, that's why some developers, they would say, oh, I don't want the tube system, I don't wanna like, these old columns in the front of the building, use shear walls. It's like, shear walls are expensive, I'm gonna pay for it, so that's, some architects, they can make it look much better with the columns. Sometimes they find a way to do it. You tell them about the system and how much it's gonna reduce the cost, and it works. Okay. All right, but this is considered as a practice. Like, this is just like to learn how the tube system is performing, how to extract the results, how to get the shear lag, and all these stuff. All right. Okay, so we are getting back to what we have been doing before, doing structure analysis again. So I want you to get in the mood back with more math and stuff like this. So all the software things we could stop like last week. All right. So if you guys remember, do you guys remember what is the last thing that we did? Before the sizing, I mean like when we do structure analysis. Before the project, we did virtual work, right? That was the last thing that was in the exam. So we are gonna continue on this topic. Virtual work, if you guys remember, allowed us to identify or to calculate the deflection at a specific point. Do you guys remember? It was something like this. And if you have, for example, a structure like this and has a specific load, and I ask you to get the deflection at a specific point. So what we do, we make a main system, and when we get the bending moment for this system, and we apply a unit load at the point that we let's say this is our main system, and we apply a unit load, and we use virtual work to get the deformation at this point. If you guys remember, right? So we used to do that. But the thing is, we didn't learn how to get reactions. So we are going to continue on this topic. It's called the flexibility methods. Flexibility method. And the flexibility method that we are going to learn today, that is called method of consistent redundance. So this is the method that we are going to learn today, and it's one of the most important methods to solve indeterminate structures. So this method basically depends on two things. The first thing is called compatibility. The compatibility is that the deflected shape is consistent with the boundary conditions or the constraints that you have here. And the second thing is that this method has to satisfy the stability or the equilibrium of the structure. And we are gonna see how this method works, how we use all this to make the structure compatible and in equilibrium. So, but before I start this method, I want to get you back to the redundance. Like, it's called the method of consistent redundance. That means, for example, let me ask you, how many redundant reactions in this structure? Two. Who are they?
The hinge.
The hinge, right? This hinge, if I remove it, the structure can be stable. But can you tell me if there is any other options for this structure other than removing this hinge? I can do something here, right? I can make this roller. So I can take the moment out and I can take the X reaction out. So that is the redundance. And if you guys remember, we did a truss before, it was something like this. And we had, I believe, something like that. Let me put roller here, and maybe I put another roller here. So, because the thing is, the main idea of this method is, number one, is to find what are the redundant forces. Because our problem with indeterminate structure is the redundant force reaction. We need to find them. Because the thing is, if this structure is like this, I can solve it, right? Fix it, 3 reactions, 3 equilibrium equations, I can get X, Y, and 1 in here. But my problem is, there is 2 redundant forces, Fy and Fx, that I want to find out. And that is what is this method is going to do. This method is going to find out what are these redundant forces. That's why it's called method of consistent redundance. So same thing here, this is a truss. So for this truss, actually, I can remove that one. That's the first redundant. And if you guys recall, what is the second redundant? This is the first redundant, F1. And this is external. And if you guys recall, that was also another internal redundant that was here, F2. So how can I know the number of redundants? Is there an equation for the number of redundants? Yes, if you guys remember, there's an IS, and you find something minus something. Depends if it's frame, truss. Once you find the IS, try to locate or try to identify if it's internally or external. So I know for sure that this is external, and there's another one internal here. When you find crosses in the truss, cross like this, definitely one of them is a redundant force. Usually the trusses is something, the vents, usually it's supposed to be something like this. If you find 2 crosses like this in the same vent, that means there's a redundant, one of them is redundant, okay? All right, so let's see how this method works. Focus with me. So let's say the same example that I put on the board. Fixed. And I'm gonna put this roller, and it has a load W. So this is, let's say this is an example and I want to solve it. Let's see how we are going to solve it using the method of consistent redundant. I put you step by step here what you should do in the notes. First one, determine the degree of indeterminacy. So can you guys tell me what is the degree of indeterminacy? 1, right? So IS is equal to 1. So basically I can remove this roller or I can make this hinge, right? So I'm gonna remove the roller, and this is gonna be my structure. And number 2 is, it says it shows a main system. Main system, I'm gonna say MS. So this is my main system. I remove the roller, and I put a main system. But before I put all the steps, I'm gonna show you how exactly this method manipulate the whole equations to get the reaction here. There's no way that you are going to get the reaction here with the equilibrium equation. But here, you can get the reactions here with the equilibrium equation. But let's think about it that way. The reactions that I have here in this problem, let's say this is point A and this is point B. What reactions do I have? I have here Y, B. Well, let's be consistent with what I have. I put here RB. So let's call them RA and RB. RB. And here I have RA. And I have a moment here, MA. I can say I have X, but definitely X is equal to 0 because I don't have any X forces. You can say XA or something. All right, so I can remove this roller and I can put this as a reaction here. If I know what is the value of RB, I can put RB here as a load. So if you solve this problem, like let's say this is a problem and this is another problem. So this one, if you put a load, external load F equal to RB, both of them should give you the same answer, right? So if you find this reaction and you solve this problem and you get the pendant moment and you get the reactions and everything, and if you solve this problem under a load F and there is an F reaction here, like an external load F equal to RB, they both should give you the same value, right? Okay. So, but let's look at the deformation. I'm going to take this system alone. All right? And what I'm going to do right now, I'm going to use the method of superposition. All right? I'm going to take this distributed load alone, W on this system, and the other system, this system, and I'm gonna put this reaction, which is F equal to RB. So the deformation of the two systems, this one is gonna make a deformation like this, right? And here you are gonna have delta, right? The thing is, this one is gonna make a deformation like this, and it's gonna have another delta. So the commutability comes here. The delta here is supposed to be equal to the delta here. Why? Because at the end of the day, you have a hinge here. So you need to find the value of the force F that is going to counter the delta that comes from this load to make the total delta equal to 0. We call this delta, we call it delta 1, oh. We call this delta 1, 1. All right? So our mission is to find the value of F force that is gonna make a delta 1, equal to the delta 1, that comes from the original system or the main system or the determinant system, okay? But the thing is, we made it much easier. What if we take this system, this one, let me write the equation here. I want to make delta 1, and I'm gonna tell you why did we call it delta 1, plus delta 1 equal to what? 0, right? The delta that comes from this system plus the delta that comes from the other system equal to 0. And by the way, we call this equation the compatibility equation. Very important equation. All right, so the thing is, we find a way that much easier to get the value of the delta 1. By the way, if you guys remember from the virtual work, and I believe you guys got it in the exam, delta 1 for this system was equal to, the cantilever was equal to, I believe, WL to the power 4 over AEI. Something like this. It has like a general equation. And if you have a concentrated load, if you guys remember, delta 1 for this system with concentrated load is BL, I guess, Q over 3 EI. Yeah, so that's like, you should memorize these values, like the cantilever, the simple beam, cantilever load was distributed load, was concentrated load. If you want to solve this, and the way that we got that, using, if you guys remember, the integration of M1, MO, DL over EI, and we used all the triangles and all these stuff. Anyway, So the thing is, this concentrated loaded F, it's much better if I have this, something like that, and I put unit load 1 here, and I get the deflection of the unit load. And I'm gonna call the deflection of the unit load here delta small 1, and I can replace delta 1 and say that delta 1 is equal to F delta 1. Is that right? So basically, it's rather than putting the full value of F, I'm gonna take only 1 unit load and get the deformation this. If F is equal to 10, I'm gonna multiply this by 10. If F is equal to 20, I'm gonna multiply this by 20, right? So if you have 100 ton here and 1 ton make 1 centimeter displacement, so 100 is gonna make 100 centimeter. Okay? So basically, I can write the compatibility equation that way. I can say that delta 10 plus F delta 11 equal to 0. That is the compatibility equation. And my mission is to find the value of F. If I found F, that means that I solved the problem, because that's the reaction that I want to find. So this is the method of consistent redundant, is to solve this equation. And the final bending moment or the final reaction is going to be that way. Like, let's say that you have here the reaction. Here, this one, this is RA, this is not RAB, this is RAO. O, that means that comes from the original system. That's the original system. And here is, oh, this is, I should have put this here, because this is the same like this one. So this is still RA. This one that doesn't have the reaction, this is the original system, RAO. And this one is called RA1. Alright? But this one is like a unit load that comes from a unit load. So let's call it R small A1. Okay? That comes from the unit load. If you want to find the final reaction, you have to sum this reaction and sum this reaction, right? If you want to find RA, is going to be equal to RAO plus RA1, right? Because this is the superposition of this two systems, like this system is equal to the superposition of these two systems. So you need this reaction and this reaction. But by the way, since you have a reaction that's coming up, this should go down. Like, I mean, if you want to be correct. So you sum both of them, it's going to give you this system. Or you can say that this is equal to RAO plus F multiplied by R small A1. Right? Because this one is just from the unit load. If you want it from the pole load, you have to multiply by F. So if you want to find reaction, bending moment is going to be that way. Like if you want to find M final, it's going to be equal to the MO that comes from the main system plus F, the force, multiplied by M1. If you want to find shear, the final shear QF is going to be equal to the shear that comes from the original system plus F multiplied by the shear that comes from the other system. So this is all the rules that you need to solve a problem like this. So basically, we divided our problems into 2 problems and we tried to solve them. Okay? So the thing is, for this equation, like the compatibility equation, which is delta 10 plus delta 11 equal to 0, it can be written delta 10 plus F delta 11 equal to 0, or we can write it delta 10 plus F delta 11 equal to 0. That is our compatibility equation. And what does delta 10 mean? Delta 10 or delta 11, the 1 means the deformation at point 1. Point 1 is this point, because sometimes you are going to have multiple points, so you're going to have 1, 2, and 3. And O means that this is come from the original loads. Like you have your system with the original loads. So anyone with the original loads is going to have O. Delta 11 means that this is at point 1, and the other one means the U2 unit load 1. So this means that the deformation at point 1 due to unit load at point 1. So if you have a general 1, delta mn, so m means the point number, point m, and this is for where is the unit load. All right. Does anybody have any question?
What is the deflection equation for distributed load?
The one that I wrote here? Really, that's your question. Okay. Well, you don't know it?
No,
Do
no.
you remember? Okay, I know. What is it?
WL to the 4th over 8, yeah.
What if it's a concentrated load?
At the end,
Yeah.
EL to the 3rd over 3, yeah.
Good job. You have a good memory, huh? Or you really remember them?
No,
No, you just
I
got
did
that
it,
from the
yeah,
word,
from
yeah.
there and
Cool. All right. So what if you have multiple? This is only one reaction. Let's say that my beam is something like this. I have hinge. Here's one roller, and here's one roller, 2, 3. How many redundants I have in this problem? 3, right? Okay, so first I'm gonna choose a main system. Let me just make a line so that we can. So actually you can choose any main system that you like, but I'm gonna choose the easiest one. I'm gonna make this one simple beam, hinge here, and roller here. Can you guys tell me where are the redundants? I have one here, and one here, and one here. So it can be, I wanna find the value of F1, and I'm gonna call this point 1, this is point 2, this is point 3. So I wanna find the value of F1, F2, F3. That is the equivalent system, all right? So the way to do it is, I have to put the original load. Like let's say I have concentrated load here, I have distributed load here, I have concentrated moment, so I have to put all these loads on the beam. Okay, that is my original system. And by the way, this original system shouldn't have these loads. This is what I want to find out. So that is called the original system. Original system. Or the main system, let's call it main system, because the original maybe you get confused with this one, main system. Alright, so the way to do it is you are gonna draw 3 different beams. This is 1, 2, 3. And you have to get these points one by one. F1, you are gonna put a unit load at 1. You are gonna put unit load here. And then the second one, you are gonna put a unit load here. And the third one, you are gonna put a unit load here. And you will try to get the deflection for each one of them.
so
So
don't you put them going up?
you can do that. Like you can, the way that I did it here is gonna give me a negative reaction. So it's still good. Like I can do it that way. The thing is, I usually put the loads going down because that's what usually I know where's the bending moment is gonna look like. So it's much easier for me. It doesn't matter if it's gonna be negative at the end, but I get the value right, and at the end I say it's in the opposite direction.
Okay.
All right, so the deflection here is gonna be something, for example, like this. And the deflection here is gonna be something like this, and the deflection here is gonna be something like this. That's the deflection of the 3 unit loads. And this is point 1, this is point 2, and this is point 3. 1, 2, 3, 1, 2, 3. So this deflection here, it is called delta 1, 1. What does it mean? This is the delta at point 1 due to unit load at 1. This one, can you guys call it delta 2, 1? The delta at point 2 due to unit load at 1. Here, 3, 1. How about this one? delta
One,
1, 2, because the unit load is at 2. How about this one? 2, 2, delta 3, 2. This one, delta 1, 3. This one, delta 2, 3, because it's at point 2. Here, delta 3, 3. At point 3, du2, unit load at 3. Okay, let's see the compatibility equation. The thing is, at the end of the day, this is not 1. This is supposed to be F1, and this is supposed to be F2, and this is supposed to be F3. But I put 1 because it's much easier to solve. At the end of the day, the delta that happens here from the original loads, like let's say the delta from the original loads is something like this, all right? So the delta that happens here should be countered by the 3 deltas that happen here. And by the way, you will see that all of them in the same direction, but at the end, you are gonna get a negative forces. So delta here should be equal to, this one is gonna be equal to F1 multiplied by this delta, F2 multiplied by this delta, F3 multiplied by this delta. Okay, so this is our first compatibility equation, that delta 1O plus F1 multiplied by delta 1,1 plus F2 multiplied by delta 1,2 plus F3 multiplied by delta 1,3. And this should be equal to 0. That's equation number 1. Equation number 2 is delta. This is delta 2O, this is delta 1O, this is delta 3O. So delta 2O plus F1 delta 2,1 plus F2 delta 2,2 plus F3 delta 2,3 should be equal to 0. And the third one, delta 3O plus F1 delta 3,1 plus F2 delta 3,2 plus F3 delta 3,3 equal to 0. That is the 3 compatibility equation. All these deltas should at the end of the day make the formation equal to 0. Why? Because there's a hinge here. There's no way that this point is going to move. So we are trying to manipulate the equation to find the forces that makes a counter deformation that counter the value of the deformation that comes in from the original load. So solving this, you can convert it to matrix. Like you can write this as a matrix like that. You can say, I'm gonna have a vector, and this vector is gonna have delta 1O, delta 2O, delta 3O. And I'm gonna make a matrix for the other deltas, delta 1,1, delta 1,2, delta 1,3, here, delta 2,1, delta 2,2, delta 2,3. And this is going to be multiplied by F1, F2, F3, and all this is going to be equal to 0. That's why usually this method is very good up to 3 redundants. If it's more than 3 redundants, it's going to be more difficult to solve unless you have a calculator that can solve 4 or 5 equations. Because basically, all what we are going to do, we are going to find the values of these deltas and the values of these deltas and build this matrix and give the number to the calculator and find the value of the reactions.
Isn't that the stiffness matrix method?
And it's very close, but this is not a stiffness method. And when we come to the stiffness method, this is not going to be a deformation matrix, it's going to be a stiffness matrix. Okay? So this is called the deformation matrix. The way to find the deltas, like any delta, delta Mn, is going to be the integration of the moment of M multiplied by the moment of N dl over EI. So for example, if we want to find delta 1O, so we have to integrate the moment from the original system plus the moment that comes from 1 dl over EI. So that's how we learn in virtual work. So what we do, so you get the moment of this system, and the moment of this system, and the moment of this system, and the moment of this system. If you want to find delta 1O, you integrate O with 1. If you want to find delta 1,1, you integrate 1 with itself. Delta 2,2, you integrate this with itself. Delta 3,2, you integrate, delta 2,2, delta 3,3, you integrate this with itself. So if you want to find, for example, delta 1,3, so you get the bending moment of 1, and you integrate 1 with 3 dl over EI. We are gonna do one in a little bit, all right? All right, I wanna tell you something that is a little bit tricky. Can you see this? What if this problem, rather than having a support like this, what is the value of the delta here?
0.
0. What if I put a spring? Before, the compatibility equation delta 1O plus delta 1 equal to 0. In this one, doesn't equal to 0. Why? Because there's a deformation here. So if I told you that this spring is gonna have K and we need to find the value of F, can you tell me how much deformation you're gonna have here? Here, like before,
0.
here, this is a spring.
No, you said there.
So
Oh.
this one, you are gonna have a deformation,
Yeah.
something like this.
Delta.
So can you tell me what is the value of this deformation?
F equals delta K, so
F is equal what?
delta K.
Exactly. And then delta is equal to
F over K.
F over K. Alright? But I'm gonna put negative here. Why? Because the thing is, the force that I want to find out is a reaction, not the internal force, and the delta is in the opposite direction of the F. So I'm gonna put negative because always in a spring, the delta is gonna be opposite in the reaction direction. So rather than having 0, I'm gonna say that this is gonna be equal to negative F over K. And definitely in the problem, I'm gonna give you the stiffness of the spring. If the stiffness is infinity, what is the value here? It's gonna be F over infinity is gonna be 0, right? So basically this equation is gonna be delta 1O plus F delta 1 equal to negative F over K, and you are gonna solve the equation normally. So you are gonna do variable separation, you are gonna get these two together, take F as a common factor, and solve the equation. This is if it is spring. Okay? Sometimes we solve the same thing with, like let's say if you decided, for example, this is not in the notes, so you might write it. Like if I have this and I have roller, and you decided to make this hinge. If you decided to make this hinge, so you release the moment like this, so you need to find the value of the moment. So the equation rather than is gonna be delta 1O, is gonna be theta 1O plus M theta 1 equal to 0. Like if you convert it from this to this, all right?
So it's not good.
What is not good? When
Well,
you
it's
do
easier.
that?
I think it's easier.
Well, it looks as much easier, but it's the same concept. It's rather than putting a unit load 1 ton, you are gonna put a unit moment 1 ton meter, and you try to find the bending moment that comes from here, which is usually negative something like this. So that is the only difference. But the thing is, what if the same problem I made like this? I have roller, and rather than giving you a fixed, I'm giving you a rotational spring. So the rotational spring, you can't remove it, because here, theta is not equal to 0 anymore. So you are gonna have this is not gonna be equal to 0. So it is the same concept. You are gonna say that theta 1O plus the moment theta 1 is gonna be equal to negative M over K. M is the moment that we are looking for here in this spring. K is the rotational stiffness of this spring, and it's gonna be given same thing. All right? Okay, I'm not gonna make it difficult that way, but you have to understand the concept that delta here is not 0 any more. Okay, so let's, I wanna tell you something else. And I believe I said it before, but I need to confirm. If you guys remember, I told you that delta at any specific point in the beam can be a combination of any delta. Can be coming from the shear, from the moment, from the torsional moment, from normal force, from everything. So the general delta on a beam has an equation. This equation is because let's say you have a 3D frame, and this 3D frame is something, for example, like this, and has a bunch of load, like there's a load coming that way, and there's a load coming that way, and there's a bending one. So if you take a cross section here, this cross section is going to have all the loads that you can imagine. It's going to have shear that way, bending moment that way, bending moment that way, torsional. It's going to have everything, right? So that's a 3D frame. So if you want to get delta, delta is going to have a contribution from every straining action, because every straining action is going to affect this this section somehow. So the general rule of delta is going to be equal to N1, like let's say we are going to get delta 1O. So it's going to be N1, NO, DL over EI. That is called normal deformation. Plus the moment MX, O, MX1, DL over EI. Plus the moment ND, and by the way, this is IX. Because if the moment is that way, you need the moment of inertia of the cross section about X. If the moment that way, you need the moment of inertia of the cross section about Y. So you have MY, O, MY1 over EI, Y. If you have a torsion, so the torsion is going to be T1, TO, DL over EI Böhler, IO. So you need to get the Böhler moment of inertia, which is the resistance of the cross section to torsion. And the thing is, we didn't include the shear yet, so it's going to be Q1X, Q1, QO, let's put the X first, so let's say QX1, QXO, DL over GAR. Alright, G is called the shear modulus, and the shear modulus has an equation, I believe 1/2 something that has the Poisson ratio. Let me put the actual equation. Here is E, Diagonal modulus, and here you definitely studied the shear modulus. I'm sure that you got it somehow in solid mechanics, mechanics of material, plus the Poisson ratio. That is called shear modulus. And AR is the reduced area, which is an alpha multiplied by the cross-sectional area, depends on the cross-sectional shape. If it's rectangle, so that's only X. So you need to get another one for Y, QYO, QY1, DL over GAR. So this is the general equation. Are we going to use this equation? No. The thing is, I did an example here. I calculated all the values that comes from the moment, that comes from the normal force, that comes from the shear force, and you can do the same thing, like follow my calculation and do it. You will find that the deformation that comes from the moment is around 95% of the total deformation of the cross section. Like I got the deformation in the cross section 0.0125. This one give me a deformation of like 2 multiplied by 10 to the power 5. And this one give me like 3 multiplied by 10 up to the power 5 negative. And this one -5. So the thing is, to this number to shows up here is gonna show somewhere here, like after you do the rounding. So it is not worth it to spend all that much time to calculate deformation that comes from forces that is gonna be like you are not gonna see them because you are gonna round and you are gonna end up with this value, right? So we usually rely on the moment deformation because they contribute to 95% of the total deformation, right?
Always, is there any case where
If you have a high shear force, like as I said before, if you have a really deep beam, something like this, and you have a column that hold 100 story or something, and you have a transfer beam, so that you can make this column not showing up, and this is really big load, so you are gonna have a high shear force, so your Q is really high, so it's gonna make this value high, okay? So this is when you have a concentrated shear force, so that's when it makes the value really high. All right, so let's solve an example and see how these principles apply. I'll ask you guys a question. Do you think it's better to write on the board or to use an iPad and write on an iPad and see on a screen and record the screen and upload the iPad later is better than writing on the board, or having the slides and having the whole material in the slides and just presenting all this in a slide one by one? What do you think what module is better?
Half and half. So like solving problems on the board, going through the problem and explaining, and also maybe if it's easier, having
Slides.
I think the writing on the iPad makes it easier to like
Yeah.
watch the lectures back.
Later.
Because sometimes it's hard to see like.
But if I
what-
did that, are you guys gonna focus during while I'm sitting? I make a lot
Yeah.
of momentum here.
You can screen record on the iPad. So it
Yeah,
goes
that's what I'm
later.
saying. It's much better,
Yeah.
like the iPad one.
Yeah, because sometimes you cannot actually see the board on the recording, so you have to rely on the notes you uploaded and the audio. So with the iPad screen record, we will both together.
All right, maybe I mean, this is for next year, so it's just like, I know
you guys are
for the feedback.
stick with whatever you have right now.
All right, so let's solve an example. All right, I give you a frame like this, and this frame is hinge, and I have this as 4 meters, 2 and 2, and this is 6 meters, and I have loads. And 3 is the loads that I have, and this is indeterminate section, indeterminate frame, and I ask you to draw the internal force diagram. For reinforcing concrete frame shown, the cross section is a rectangular section with width of 20 centimeter and depth of 40 centimeter, and the E of the cross section, the Young's modulus is 200. The material of the cross section is 210 ton per centimeter square, and the Poisson ratio is 0.2. All right, so I solved this problem with shear deformation and normal deformation and bending deformation. But what I'm gonna do now, I'm gonna only solve this section for the bending deformation. But you can check how the normal deformation I did it here. Same sequence, all right? So if I wanna do it with the normal shear moment, I have to draw the bending moment diagram, the shear force diagram, and the normal force diagram, all the diagrams. I have to do that. But if I'm gonna do only bending deformation, I only need the bending moment diagram. But let's draw the 3 of them. So the thing is, to solve this problem, I told you you have to choose a main system without the redundant. So you can pick this can be redundant, or this one can be redundant, like the Y reaction here. So what I did here, I picked this system with roller here and a hinge here. That is my main system, and I put the original load, the 6 ton and the 3 ton. So that is my main system. So first you have to solve this main system. What do I mean by solving this main system? You have to find the reactions here. So you have to find what is the Y reaction here, what is the X reaction here, what is the Y reaction. The easiest one is this one. What is the value of the X reaction? You have 3 ton here, and the only way to resist it is with another 3 ton. So what happens here, this 3 ton is gonna make a moment that way, and this 6 is gonna make a moment that way. So you have to take the moment here to get the reaction here. solve it without like doing the equilibrium? Okay, the way that if I wanna do it, let's see if it's gonna work or not. This 6 is gonna be divided into 3 and 3. So you're gonna have 3 here and 3 here. But this 3 with 3 is gonna make a couple that way that make this force, like the thing is this 3 with the 3 is gonna make a moment that way. So it's gonna compress this hinge more, like it's gonna make a more compression on this hinge. So I would expect this is gonna be plus you need a moment that counter this moment. So you need a moment, this is gonna make that way. So I believe you are gonna have a Kessler reaction here and another one here that counter this moment. So 3 multiplied by 2, 6 ton-meter. So you need another 6 ton-meter that counter the moment here. Is that 6? This is 3. So 3 meter and 3 meter. So this is 3 multiplied by 2. So it's gonna give you 6, and you need another 6 ton-meter couple. So you need 1 here and 1 here. So what happened here is, I'm just trying to think as an engineer, how is the moments is working. This 6 is gonna be divided equally because it's in the middle, 3 and 3. And this 3 ton-meter is gonna make a couple that way. I need a counter couple on the other side. So I have a 1 going down and a 1 going up to counter this couple. So 3 plus 1 is gonna be 4, and this is 3 minus 1 is gonna be 2, and this is 3 plus 1 is gonna be 4. So at the end, once you solve this using the equilibrium, definitely you are gonna get 2 here and 4 here. So when you do sum Fy, 2 plus 4 is gonna give you 6. Alright, so I got the reaction, okay? But the safe way to do it is to get the moment at A. Like let's say you are gonna get the moment at A, summation of the moment at A should be equal to 0. So getting the moment at A we don't know what is the value here in the reaction, so you are gonna end up with, I'm gonna assume that the positive that way, so 3 multiplied by 2, plus 6 multiplied by 3, the moment of this,
Minus.
and this minus, you have a 3 here, so this 3 is gonna be minus 3 multiplied by 4, and this one is the reaction that I'm looking for, so this one is gonna be negative, the reaction, let's say, y, multiplied by the distance, which is 6, equal to 0. 3 by 2,
Minus 12.
minus 12, and 6y equal to 0. So this is gonna be 18, up really. Oh, 6 plus 18 is gonna give you 24. 24 minus 12 is gonna give you 12 positive. You can send this, so y is gonna be equal to 2, which is this one. And then you get summation Fy and then you get 4. That is the safest way to use the equation. Alright, so let's get the bending moment and the shear force and the normal force diagram. This is a structure analysis problem, so let's put this as ruler, hinge, another one here, and another one here. I'm gonna draw here the normal force diagram, the shear force diagram, the bending moment diagram. Alright, let's take step by step. Here, what is the normal force here? At this section? 4, positive or negative? It is compression. It's come to this section, it compressed at this section. So I have 4 here. So I'm gonna go, it is negative, so I'm gonna go inside and I'm gonna put negative 4. And the value here is negative 4 until I go up there because there is no any force that can change this 4. So this is positive, I mean like compression all the way up. How about this one? What is the value of the normal force here?
3.
3, and it's compression or tension. Compression, because it goes inside the section, not outside the section. So I'm gonna have 3, and it's gonna be all the way until I come here because there's no any other force. So this is gonna be -3. Okay, I'm done with the normal force. How about the shear force? Is there any force that makes shear here? No, because there is no any force here because this is roller. So the shear force is gonna be 0, 0, 0 until you come here. Before the 3, it's a 0. After the 3, the shear force is not 0. And the thing is, like the convention, the sign convention, you put yourself here inside the frame, right? And you look, here's the cross section. If the shear force is going up, it's gonna be positive. If it's going down, it's gonna be negative. So I'm here, and the shear force is going down here this way, so this shear force is negative. It's gonna be -3, something like this, and it's gonna be all the way up because there's no any other force. So this is -3. All right, how about here? Here you have a 4 going up, so that means it's positive. So I'm gonna go 4. I'm gonna go all the way until the 6. The 6 is gonna take the 4 all the way from +4 to -2. Because I'm gonna go down,
Yeah.
and then I'm gonna go constant until the other 2 bring me up. So that is the shear force diagram. All right, bending moment diagram. Here the bending moment is 0 until I come here, and here is the bending moment where it's gonna start when I go away from the street. So the street is gonna be multiplied by 1. So the value of the moment here is gonna be 3 multiplied by 2 is gonna be 6. So I'm gonna come here, and this is a negative bending moment because the positive is that way. So this is making negative moment like in the other direction. So this is gonna be -6. How about here? The bending moment is 0. The more that I go away, the more the 2 is gonna make a bending moment, and this bending moment is gonna be positive bending moment. The thing is, this 2 is gonna make a bending moment that way, so that's positive. Or if you wanna do it from here, so you're gonna have this 4 is making a bending moment. So, but anyway, so the bending moment, since you have a force here, so this is gonna be something like this, something like that. But the thing is, let's be consistent and make the positive up and the negative inside, because I make the negative inside, so this is gonna be something like this. Check. Yeah. The values here is gonna be 6 Nm, because the thing is 2 is gonna be multiplied by 3 is gonna give you 6 Nm, and the value here is gonna be 6 Nm to counter this value. So this is positive, and that's the bending moment. Did you guys got it? By the way, if you don't know how to get the bending moment, shear force, normal force on a beam, on a frame, on a truss, that's a major issue for a structural engineer. Any beam in the world, I mean like determinant beam, I'm not saying about indeterminate. Sometimes indeterminate can be tricky because you have to calculate indeterminacy. But if there's a determinant structure, you cannot get the bending moment and shear and normal, that's like, I don't know, like big companies, they have to ask these questions, they have to give you something, and he will tell you, sketch the bending moment. You don't have to calculate it, sketch it. You have to imagine it, you have to know how it's look like. If an indeterminate, like if I have an indeterminate section like this, that's indeterminate, and I have a bunch of load, let's say it has this load. I don't have to get number, but I have to have imagination. How's the final bending moment is gonna look like? You should know that. Like for example, this one, I know that this is like kinda is gonna give me a bending moment like this here, something like this. But the thing is, this is fixed, and I need to counter this bending moment, so you're gonna have like some bending moment, something like that. So this is, because this is fixation, and this is how the final bending moment look like. If this is hinged, like something like this, and you have hinge here and hinge here, so same problem is gonna be something like this, but the bending moment is gonna go to 0. Because that's how you sketch the bending moment. As a structural engineer, you should be able to sketch the bending moment on any beams or a frame. try to sit with yourself 1 week or whatever, try to revise the concept of structure analysis and put any beam in front of you and try to solve it on your own. Because this is, if you don't know how to do this, that's a major issue for a structural engineer, and you are a graduate student, you should be able to do this. Try to sit with yourself, revise all the basics, how to draw the bending moments, and put any beam, make any shape in the world, and you have to be able to draw the bending moment and the shear force diagram. Because without this, without the basics, we are nothing. Like without doing this, what are we doing if we don't know how to get a bending moment? Because that's what we all do. As a structural engineer, we design for bending and shear and force. Whatever the software you are using is using its same principles. Okay? Alright, so we got the shear, normal, shear, and bending moment. So let's get back to the main problem, that we need to find the redundant. As I said, I'm not gonna calculate the normal and shear deformation. I'm just gonna only focus on the bending moment. In the notes, you'll find that I did this and that, and I get the value for them, and you're gonna see that the value is very small compared to the bending moment. All right, so let's focus on the bending moment. This is the main system, and I have the roller here, and I have the hinge here, and this bending moment, I have something here, and something like this, and this is 6 ton meter, and this is 6 ton meter. So this is MO, the main system bending moment. We need to find M1 that comes from, all right, you will draw the same system after taking the original load out. I'm gonna take the 3 out and the 6 out, this 6 and this 3, and keep the main system, but I'm gonna put a unit load at the removed redundant. Where's my redundant? What did I remove? Look, this is roller, this is hinge. What I removed is the X reaction here. I assume that X reaction, let's say X. This one, that's what I want to find the value of this X. So you put a unit load here, 1 ton, like this. And the thing is, when you put this that way, you are gonna have a reaction here equal to 1, and these two is gonna make a couple that way. So you are gonna end up having a reaction going down here, and a reaction going up. I would assume this is gonna make 1/4, so this should generate 4, and the distance is 6. So I believe this is gonna be 4/6, and this is gonna be 4/6. If you wanna get the right value, do equilibrium equation. Get the moment here and make it equal to 0, and find the reaction is gonna be 0.67 and 0.67. All right? Okay, so here, this value is negative, and this value is positive. All right, so I got the reaction. You can draw the bending moments. Can you guys tell me how can I get the bending moment of this frame? What is the moment here?
0.
How about the moment here? Something, what it is?
1 times 6.
1 ton.
1 times
4, sorry.
4. Yeah, this one is 4. So, is it positive or negative? Set yourself here. And you are inside, and this load is gonna make a bending moment that way, so it's gonna be negative. We put the negative inside, so we can make this something like this, and this is gonna be 4 ton meter. How about the moment here? It's a hinge, the moment is 0. Here is the 0.67 multiplied by 6. So it's gonna be equal to 4 ton meter. That is negative and negative. By the way, the sign is very important. And let me draw this right because the 6 is in the middle. So I'm gonna make this. So right now I have MO and I have M1. So I want to solve the compatibility equation. Delta 1O plus F. Delta 11 equal to 0 because I have here hinge. There is no springs. Okay? So this is equal to 0. So if I found delta 1O and I found delta 11, I solved the whole problem. So how can I do this? Delta 1O is going to be the integration of M1 MO dL over EI. Okay? All right, so what I'm gonna do, do you guys remember the table that has the triangles? You're gonna do the same thing. You are gonna divide this into triangles. You are gonna have, this is the first triangle, and you are gonna integrate it with this triangle, the one in the middle here, which is have 2 meters. This triangle with this triangle. And this is gonna have 2 triangles and they are equal. I'm just like draw it not right, because you have 6 and 6, and this is 3. So you are gonna make this with this trapezoid, and you have another trapezoid here. This one, you are gonna integrate this triangle with this trapezoid here. Did you guys got that? You have to divide this into pieces and integrate the triangles together. Go to the table, I believe 10 in the textbook, in the table 1 in the appendix, and see integration of a triangle with a triangle with a trapezoid, and this is a triangle with a trapezoid, and pay attention to the sign, because this is positive and this is negative. And sometimes this is negative and this is negative. When it's a negative, it's gonna be positive. But if it's a positive with negative, at the end, the integration is gonna be negative. All right, so I need to calculate I of the cross section. Can you guys calculate the I of the cross section? I wanna find the value of I that resists that moment.
20 times 40 to the third over 12.
20 times 40 to the power
3.
3 over 12. That is the moment of inertia of this cross section about this axis. If I want to find the other axis, so it's going to be 40 times 20 to the power 3 over 12. And then you find this value. And pay attention, this is all centimeters. So at the end, you're going to have this centimeter to the power 4. And E is equal to 210 ton per centimeter squared. So everything is going to be ton centimeter. So once you solve this, you are going to find that delta 1O okay, I did the calculation here, like I put every piece, so you put every piece one by one, and at the end, once you calculate this, it's going to be equal to 0.10 here, 0.01026 meter. That is the value of delta 1O. The value of delta 11 is much easier than delta 1O, because you are going to integrate this with itself. You only have 2 triangles, this one and this one. If you don't know what I'm talking about, go revise the virtual work method and see how we can calculate deformations. So delta 11 is going to be the integration of M1 with M1 dl over EI. The value of EI, let's put it here. After I did my calculations, 2240 ton meter squared. I converted from centimeter to meter. Okay, so once you did delta 11, you are going to find that this value is 0.0234. By the way, delta 11 that comes from the normal force. If you calculate the normal force N1 dl over EA, the one that I said I'm not going to do it, like the calculation here, look at it, 4.64 multiplied by 10 to the power negative 5 meter. Wow. So the thing is, this force is not going to show up here until you come here, like until like this one. So it's kind of like not that important. So the most important one, the one that comes from the bending moment. All right, so right now I have delta 10 and I have delta 11, so I can put them here. So 0.01026 plus F multiplied by 0.0234 equal to 0. So F is going to be equal to negative over 0.0234. So this is going to give us F equal to negative 0.452. What does the negative mean? That means that I assume the unit load 1 in the opposite direction. So that means that the reaction should be in the other way. So So here's my frame. It's gonna be something like this. And this is the hinge, and here's another hinge. I found the value of the reaction here equal to 0.452. That is the value of the reaction. How about the values of the reactions here? This one and this one, and I know this one already because it's supposed to be equal to this one, 4.52. If you want to find the value of these two reactions, let's say this is Y1 and this is Y2. Y1 should be equal to YO plus F multiplied by Y1. YO is the reaction from the main system. This one, the 4. Okay? So I'm going to put this as 4. Plus F, which is negative 0.452, multiplied by Y1 is the reaction that comes from this system, which is 0.67. And this should be equal to 3.7. So this one is 3.7. So basically it went down a little bit from 4. And you should find this one. By the way, you can find this one using the same method. Y2 is equal to YO plus F multiplied by Y2. But I can do some Fy since I know that this is 6. So this should be 2.3. Alright, summation Fy should be 2.3. Okay, so I found the reactions. Once I found the reaction, I can find the bending moment. So you can find the bending moment by getting the bending moment section by section. But here in the middle, because you have 6. 6 ton and 3 ton. You can find the bending moment shear normal for this, or you can use this equation. The moment at any cross section, M final, is going to be equal to the M that comes from the original load plus F multiplied by M1. So you have this moment and this moment. So the final moment is this plus F multiplied by this. So if this is 0 and this is 0, so the moment here is going to be 0. You want to find the value in the middle here. This is 6 centimeter positive minus 0.45 multiplied by -2. So negative is going to be positive. So I expect the 6 is going to be a little bit bigger. So the 6 actually is 6.9 right now. All right, or you multiply 2.3 multiplied by the distance, which is 3. 3 multiplied by 2.3 is going to give you 6.9. Same thing. Try it that way and try it that way. And then you get the value of the moment here. You can do the same thing. Here's the value of the moment is 6, and it's negative, minus 0.45 multiplied by -4, so it's going to give you positive. This is negative plus positive, so I can imagine that the 6 is going to go less than 6, so it's going to be 4.2. So this became 4.2. Or actually you can get the moment here by 2.3 multiplied by 6 positive minus 6 multiplied by 3 negative, and you find the value is going to be equal to 4.2. Same thing here. You are going to find the value. The moment here is going to be 0, and then you are going to have a moment here and a moment there. So this. But this is going to be in the opposite direction, because the thing is, before I assumed that the force is going to go that way. Right now it's that way, so the moment here is going to be positive, and it's going to be something like this. 0.452 multiplied by 2, so I believe it's around 0.9 something. And this definitely should be equal to 4.2 without any calculation. Why? Because if this is 4.2, this has to be 4.2. They have to have the same bending moment for the stability. So this is positive, and this is negative. Sorry, this is positive too. So I'm gonna make this, and these are the negative bending moments. All right. You can do the same thing to get the normal force diagram. But I would, to be honest, the much easier for me, if I have the reactions here and everything here, I use this to calculate the bending moment. Just find the new reactions and then get them section by section. All what I need the value of the moment here, here, and here. These two are 0, so basically I need 3 points, and I connect between them. Like this. That's how I draw the bending moment diagram. So for now, I finished the method of consistent redundant method. There is definitely in the midterm, the final exam, there's a question on this, has 25 points. Try to revise and understand this very good. Think about it as steps. Step 1, choose a main system, determinant and stable. Find the redundance. Get the bending moment for the main system. Get the bending moment for the virtual system that has the unit load. Integrate them, get delta 1,1 and get delta 1,0. And then substitute in the compatibility equation. That's for any problem. If you do this step 1 by 1, you are getting 5 point, 5 point, 5 point. If you mess up with 1, you're just gonna lose point in the one that you messed up with. So choose the main system right, get the bending moment right for this system, and then choose the virtual system. Not choose the virtual system, build the virtual system, and then get the bending moments for both right, and then solve for delta 1,1 or delta 1,0. In the exam, I'm not gonna give you more than one reaction. Only one equation. The one that has 3, I'm not gonna give it to you. Just one. Maybe it's gonna be a B, right? So here, try to practice. I solved it at frame. It's a little bit difficult. Maybe if you can solve it, that's great. But if you can't, that's fine. I put some beams that has a springs. So you are gonna find someone that has a spring. And I have another one with a spring. If you need more, I can send you more. But this is enough to understand the concept, right? So next time we are gonna do the stiffness method, okay? All right, so I'll see you guys next time. Thank you.
Yeah. Bye, thank you.
Pasado de editor, pues. Pasado de editor, pues. Bueno, yo no sé. Hágalo ya. Nada más replicable ya, eso tiene que tomar más de 20, 15 como. Mira, yo lo tengo en el piso de. Tú le das
Yeah, I have it right there.
a 20 o como tú te reparas. Después, yo creo la sección. Ahora uno puse